Hi everyone. So in this video we'll discuss the interpretation of the analysis that we had in the last video on approximating the cost function and using this approximation the effect of early stopping on the obtained solution, right? So we ended up with having this expression right here, which basically says that if you project the parameters obtained, if you initialize first with parameters equals 0, right? And then if you project after tau time steps, if you project this on Q, which is the matrix of orthonormal eigenvectors of the Hessian, right? So it's a representation basis for the vector space containing W, and this basis is basically in directions corresponding to eigenvectors of the Hessian of the cost, unregularized cost with respect to W evaluated at the unregularized minimum. So if you have this projection on Q of the parameter setting obtained after tau time steps, this is the same as projecting the unregularized optimal and then scaling in every direction, scaling the parameter in every direction, the projection of the parameter on each of the bases by this value. And remember that this is basically a diagonal matrix where each element equals 1 minus epsilon lambda I to the tau. Okay? And we noticed that this is, and that's what's interesting about it, is that this is equivalent to what we got through a similar approximation on the solution obtained through L2 regularization, right? And basically you get that they are equal if I minus epsilon lambda to the tau equal lambda plus alpha I inverse times alpha. So both of these are diagonal matrices, so the equality ends up being element by element equality. And if you take the log of both sides, so this is basically alpha over lambda I plus alpha, and this is 1 minus epsilon lambda I to the tau. If I take the log of both sides, I get this equality right here, which is tau log 1 minus epsilon lambda I equal minus log 1 plus lambda I over alpha. Now, let's make one further assumption, one last assumption to simplify that expression and draw a simple interpretation. So if the lambda is very small, right? So meaning that the curvature, lambda is very small, meaning that the curvature of the Hessian around the unregularized optimal is very small in all directions, right? And in many cases, actually, this is where regularization makes sense, because that means that the cost function doesn't change very quickly if I change the parameters slightly from the optimal ones, right? And that's what regularization does. It perturbs the parameters from the optimal to improve generalization, right? So that relies on an assumption that the cost function will not change by much. The unregularized cost will not change by much if I perturb the parameters slightly. So if the lambda is very small, then we can use an approximation which is basically says that log 1 plus x is can be approximated as x if x is very small, right? And in this case, what you will get is basically tau times minus epsilon lambda I equal minus lambda I over alpha. And you can cancel lambda I from both sides, and you get that tau will be approximately equal to 1 over epsilon alpha. Now let's remember what each of these correspond to. Tau is the number of time steps after which early stopping stops, right? Epsilon is the learning rate. Alpha is the L2 regularization coefficient or weight decay coefficient for the L2 regularization. So that means what? That means that under all the approximations that we have done, and we will reiterate again in the next video over these assumptions, the assumptions behind these approximations, just to make sure that it's clear to us when this will hold, right? But under these assumptions, then early stopping, when it stops after tau time steps, it's basically equivalent to L2 regularization with the regularization coefficient equal alpha, and alpha is given by 1 over epsilon tau. So actually, let's make sense out of it first. So if the more aggressive the regularization coefficient that L2 has, the earlier the equivalent early stopping mechanism will stop. And that makes sense, because early stopping is more aggressive if it stops earlier, right? Now, let's make sense of the epsilon here. If epsilon is large, then for the same alpha, I would stop earlier. And that makes sense, because epsilon is large, that means I'm making larger steps, so I'll stop earlier. If epsilon is small, I'll stop later, right? So what's the advantage of this? If we know how to do this with L2 regularization, what's the advantage of early stopping? The advantage is that we decide on tau dynamically. In L2 regularization, I have to, a priori, I have to decide what alpha is, right? So this is like an automatic way of hyperparameter selection, where the hyperparameter here is the L2 regularization coefficient. So remember, we said one of the motivations for early stopping is that it's an automatic way of selecting the number of training time steps. Here we are drawing an analogy between the number of training time steps and the L2 regularization coefficient, right? So this is saying I can automatically, by doing early stopping, I am implicitly doing an automatic L2 regularization that chooses the best regularization coefficient for this training data, right? And that's basically it. So that's why it's a very advantageous, and you see it much more common in deep learning, and especially for deep learning, because the number of parameters is typically very large. So and the training time takes a lot in many cases, because these models are complex. So if I were to do L2 with multiple regularization coefficients, that would be very costly in terms of computation, right? But early stopping, it's very simple. You hide part of the training data as validation, and you stop whenever you get, and you choose the parameters that led you to the least validation loss, right? So this analogy is saying that when you do that, you're basically choosing, it's as if you're implementing L2 with the best regularization coefficient. What does it mean, best regularization coefficient? It means best generalization performance with respect to the validation data that I did hide from the training process, right? So, let's, as a final note before we finalize, remember that like L2, here also the parameters corresponding to directions of significant curvature are regularized less. Why is that true? Because if you look here, right, the parameters where the cost function is very sensitive to changes will have a large alpha I, right? So 1 minus epsilon will have a large lambda I. So 1 minus epsilon lambda I will be small, right? So I will subtract from the diagonal, the identity matrix, a very small, and a matrix, a diagonal matrix with very small elements. So the change that will happen to omega star will be very small. So regularization will be much less aggressive. In directions where the lambda I is very small, the regularization due to early stopping will be much more aggressive. Okay, thank you.